dan, dobre što predošli. Thanks Armada JS team, it's an amazing conference, and thanks Miro for announcing me. I'm lucky today because I get to talk about two awesome topics. One will be a little bit hardcore, and another one should hopefully be fun. And if you missed Bibi's digital talk yesterday, she actually did like a nice intro for WebAssembly. If you haven't seen it, I'll do a quick recap of like what WebAssembly is. And the first thing, well, it's not just for web, and it's not exactly an assembly, so the name is kind of misleading. But the cool thing about it, it's an intermediate representation, and you can compile from almost any type language into WebAssembly, and then you can run it pretty much anywhere. So you can run it in the browser, and JavaScript engine would actually run it, so it can operate with JavaScript. But you can also run it from other languages. So, for example, Ujwal, he's not here, but he's working on a tool which basically allows it to run anywhere. And you can also run it in the cloud, which is a pretty cool thing. And fun thing, it's very, very simple inside. It can only operate on 4 types. There actually are more types. There are like functions as first-class citizens, but at this point, we only care about 4 types, and all of them are numbers. It has a binary representation, and this is a real WebAssembly program, or maybe not. Nobody can check that. So, and it also has a text representation, and this is what we are going to spend lots of time on today. So it might look a bit confusing, but we will dive into it, and hopefully it won't be. And the second thing, which I'm gonna talk about, and we'll merge them together, is called cellular automata. Who have heard about this thing before? Few people. Perfect. It's extremely simple, and simple like a cell simple. It starts with just a cell, which can has states. In our case, just black or white. And 2 more things we need to make automata out of this is actually a grid and rules. So once we have that, we basically get some kind of interesting behavior. To make it even simpler, I'm gonna take a very small grid, just 9 elements, and I'm gonna take very simple rules. White turns black, black turns white. I'm gonna hit play button, and anybody has any expectations? This happens. Pretty straightforward. I'm gonna put a bit more complex rules on the screen. Now we're not just looking for the previous state of the cell, we actually are also looking for the state of its neighbors. So I'll give you like 15-20 seconds just to think through what would happen. If anybody knows what's gonna happen, raise your hand. Okay. Okay, so anybody who hasn't seen my talk before knows what's gonna happen? All right, I'm gonna hit play. So this is gonna happen. So we can see all the rules go into white, except this one, where the cell is on the left. Does it make sense? Cool. Here's like a more complex rule. I'm not asking you to predict it, but it will be like a bit more interesting. It definitely makes more sense if you make a 2D plane out of it, and then every step you would put on the next line, and we are going to see this later. So those rules are very simple. Cells are very simple. The question is like, how complex can be the behavior produced by those cells and rules? And those 2 guys think it can be pretty complex. Anybody recognizes anybody on this photo or no? So the person on the right, his name is Stephen Wolfram. He's author of a thing called Mathematica, and he wrote a book. It's called A New Kind of Science. It's a very, very long book. It's thousands of pages. It's a bit controversial because he published it himself, but basically what he did is he took all possible combination of rules, and we can see there are 8 possible neighbor combinations. Each of them is 1 or 0, so 2 to the power of 8 is 256 rules. That's basically it. And then he categorized them, and then he thinks that it's a really big thing and will change the way humanity does science. And the idea here is what we often do in, let's say, physics, is we have a formula. And if we want to predict state of something in the future, we basically apply this formula based on t as a time, and then we get some kind of number. But this is not how things work in real life. And here, if you want to see what happens on a step 100, you have to calculate 99 steps before it one by one, because everything depends on everything. So the behavior becomes like really, really complex. And this is what makes it fun. And we are gonna see it a bit later. And the second person, his name is Richard Feynman. He is a physicist. He is not exactly a programmer, but he is like super smart person. And this is my second book recommendation for today. It's like one of my favorite biographies ever. I see like Mira is nodding. It's called Surely You're Joking, Mr. Feynman. So besides being super smart person, he actually really like jokes, and he did lots of like really funny stuff, and he played like pranks on people before it was popular on YouTube. So there is a long quote, which I'm not gonna read, but Wolfram was, out of all those rules, really excited about one called Rule 30. And the reason was because out of those simple rules, the behavior which was produced was like extremely immensely complex, and it was proven that it's some kind of chaotic behavior, whatever it means. And Richard Feynman, who was really interested into that, tried to understand this, and he and his son, they spent like lots of time trying to crack like why this behavior is so complex. And at some point he just called Wolfram and said, okay, listen, I give up, it's too complicated, and then he never touched it again. So of course we're gonna see, like all of us want to see this Rule 30 and like why it's so interesting. Okay, so who here, there is IKEA in Serbia, right? Okay, so we'll have to build it ourselves with WebAssembly first before we can run it, just like in IKEA. And let's look in this text format which we're talking about. So the simplest WebAssembly program we can compile and run is this. It's just module. It doesn't do anything, but it works. It's a real thing. And then we have a function. Let's start with a simple function add. It has 2 parameters. First parameter is x, and WebAssembly uses types for everything, so we can say it's a 32-bit integer. Second parameter is y, and then result is basically an integer. So in regular language, we would go something like return x plus y, and of course in WebAssembly this would not work. First of all, semicolons are not a thing, so people who like JavaScript enjoy semicolons, I have good news for you. You can use double semicolon and then it becomes a comment. So people who like really miss semicolons just put like double semicolons in every line. Second thing, like in JavaScript Lambda functions, we don't need return. The last statement basically gets returned as a function result. And third thing, we have $signs, yes, just like in PHP. So I'm gonna add those. And next thing is if you are using any variable, you're gonna use a get local thing. So this basically means take a value of this local variable x, and then we take a value of local variable y. The last thing is we're gonna do something a bit weird. We're gonna put add function after everything, and now this should work. Okay, it's local.get. And then boom. So now we have add function which basically adds 2 numbers. So what's the deal with all this like add function coming after arguments? So the thing is that WebAssembly is stack based. So we're gonna have a quick intro into stack based programming. I assume most of you know what stack is, but it's a very simple data structure. You can think of it like a Pringle box where you could put some apples and strawberries, but you can only take or put the last element. So here is an example. We can only operate on strawberry at this point, and it has like 3 simple operations. First of all is pop. So we have 5 apples, and here's the little exercise. We only want 1 apple. So I'm gonna just press this button multiple times, and boom, I got 1 apple. If you take something from the stack, you can use it. Like I could eat this apple. The next thing is push. So it's like you would be putting apples in Pringle box. I don't know why. I'm gonna put an apple, a lemon, and an apple here, and here we go. I'm successful again. Nice. And the last operation is pick. So sometimes you wanna like look what's there and just put it back, and you don't wanna do like 2 operations, and this is why pick exists. And it basically says, yo, it's a lemon. Congrats, that's good. Now little practice. So have 2 apples, and we want to get strawberry and lemon. So I'm gonna pop 2 of them, and then push 2 of them. And here you go. So by this time, you're pretty much stack expert. There is an exercise. So there are like 2 companies, most of you probably know, which only one of them has stack on their logo. Who can tell me which one? Okay, it's Stack Overflow, and it's also Overflown, which is pretty cool. I realized it like only recently, and my mind was blown that there is Overflow and Stack on Stack Overflow logo. And what Stack Blitz is doing, I have no idea. So now we all know stacks, and now it's time to learn Stack Machine, which is a principle which is used in many programming environments, including WebAssembly, but also like JVM, Java bytecode. And the idea is we have functions which can pop things, and then they can push things based on the stack. So to get a pineapple, you're gonna push pine and apple on the stack, and then you run this function, and you'll get a stack with a pineapple. Let's do an exercise. We're gonna get this lemonade, which takes the following ingredients. The order is important, so I'm gonna put cherry, water, and lemon, and then I run this function. Boom, I have lemonade. And this is pretty much what WebAssembly is about. You put 3 things, and then you run a function which takes 3 things, and you get another one as a result. And this is how our add function works. So now it's time for coding plan. So what we're gonna do is we're gonna write a bunch of functions in WebAssembly text format, and this will be a bit hardcore, and also generally like you would not do it yourself, but it will help you to understand what is inside of WebAssembly, which is the topic of this thing, and then in the end we'll see all those like Rule 30 and all the cool things. So the plan is for every cell, we're gonna look at its 3 previous states. And one thing important here, like when I was a kid, there were like 2 kind of games. One like Pac-Man, when you go to the side and then you appear from the other side, and like if there is somebody chasing you, then you basically run away. And another one is like you go to the side of the screen, and then somebody's chasing you, and then you're basically screwed because there is a wall there. So we have the second kind of behavior, the first kind of behavior, where this cell, everybody sees my cursor, right? Is gonna look for this, and also like this side. And also we are gonna represent our behavior as functions. So we'll have 8 functions with 0, 1, 2, 3, 4, and each of them will return either 0 or 1. And by its functions is just so I can explain some concept of WebAssembly better. So we will start with a function called rotate, and I'll just live code it, and let's see how it goes. It's gonna take 1 parameter, which I call x, and okay, let's take another parameter, which I call row size, where row size would be 9. It's basically the size of the grid. And immediately WebAssembly starts complaining. I have this panel on the right which displays the result. And is it big enough? Can probably make it a bit larger. And basically what it says is, this function says it has a result. I see no results, put something on the stack. So I can put a number just to start with. In WebAssembly, you cannot do 5 because there are 4 number types, and WebAssembly doesn't know which one is 5. So you have to say which one it is. In our case, it's 32-bit. And boom, we have 5 tests, which we have 4 tests, which we have to pass. And the first one is very simple. We call rotate with 0 and 5. So what rotate is gonna do is gonna look at the x coordinate, and then if it's out of bounds, so for example, we're checking the last cell, which is y, and then we check for the previous value, for the immediate value below, and then the next one is kind of out of bounds. So we're gonna just shift to 0 because we want to see this function. But let's start with a simple test. We are here, and the x is 0, and we want to get 0. So here we just return x. And this immediately passes the first test. The second test is we're basically gonna divide it, use like modulo, and get a reminder of dividing by the row size. So I do local get row size. And then, like all things, you start with like i32, and then you say rem for reminder, and then it can be either signed or unsigned. In our case, we don't care, so we can use signed. The next thing is pretty much the same, except now we're on the left. So we are looking of the neighbor with a cell with x0. So one of them will have coordinate position -1. So the way we fix it is we basically just add row size before getting a reminder. And now all the tests pass. So this was a simple function. The next one is we're gonna make row size global. I just pressed the magic button so I don't have to write it out. And now we have row size coming from external environment. We don't know what it is, but basically we're telling WebAssembly that there will be a configuration object passed to this thing, which will have property config, which will have property row size. I have a bunch of JavaScript which is running this thing, and you can see here I have a config object. It has a property of row size. The value is 5. And then at some point when I instantiate WebAssembly, and this is a lot of code, so just focus on what's selected. I instantiate WebAssembly, I pass the code and this configuration file. Now we can basically access this object in WebAssembly and get all the values from it. So before I was using local variable, now I'm going to use global. And global here, and boom, all tests are passing again. So the next function I'm going to write is also pretty simple. It's called getIndex. And what we're going to do, we're going to work with memory now, and in order to prepare, we are going to take 2 coordinates, which are x and y. And we are going to turn it into index in memory. I'm going to return just like any constant just to get the test running. So the way stuff is represented in memory, and WebAssembly has access to raw memory. So you can just say like, get me something at the position 0, and you cannot do arrays like you would do in JavaScript. So we're going to just convert, we're going to look at x coordinate y and find the intersection, the position of in memory. And we start with just returning x. And it should be local get x, which immediately passes a couple of tests. The interesting thing now happens when we have a y coordinate. So what we're going to do, we're going to multiply y by the size of the row. So I'm going to get y. I'm going to get global row size. And I'm going to multiply them. And then I'm going to take x and y, and I'm going to add them together. Boom. That's basically it. We have like a more fancier test where coordinates are 3 and 3. but basically it's x plus y multiplied by row size. So if we were writing it in JavaScript just to compare, it would be like x plus y multiplied by row size. So you can see that the WebAssembly is kind of like a bit more verbose than JavaScript. And the next thing we're gonna do, since we are going to evolve multiple rows, we're gonna have a step which will be a global. But unlike what we did before when we like imported it, we're going to export it now. So this means that this global variable will be available in JavaScript. So if I scroll to JavaScript, once we instantiate WebAssembly, we get result thing, which has an instant property, which has an exports property, which will have all the stuff which WebAssembly exports. So we can go with like result export step, and then we get the value of it. So this is how JavaScript would operate with WebAssembly. And one other thing we're doing, we're defining initial value, which is 1. And we're also saying that it's not just a number, it's a mutable number. So we can update this number from WebAssembly. And next thing we're gonna do is we're gonna add some memory. So memory is also shared with JavaScript. For those familiar, it's uint array. It's basically just a buffer, so you can access it from JavaScript and it will look like it is an array. So there are like 2 lines here. First of all, we just say, yo, there is a memory. And 1 here, it means the size of the memory in pages. 1 page is 64 kilobytes. I can use 10. There was like a famous quote which was attributed to Bill Gates. At some point he said like 640 kilobytes should be enough for everybody. I don't think it's real. Like he denied that. But it's still funny and it still haunts him until now. So we're gonna have 640 kilobytes of memory for our thing, and then we're going to export this memory. So that means we can interact with this memory in JavaScript, and it is available on result instance export memory. We here convert it to an array, and then what we're doing, we're basically setting one of the cells, just the element in the middle of the array, to 1. That's how interaction works. And next thing we're gonna do, we're gonna get a function which will take a coordinates and will load these values from the memory. It's basically look into this array and see if there is 1 or 0 there. So the function is here. It's gonna take x and y. And then we're going to, what we're going to learn here is how we can call a function, which is literally you say call and then you put function name. And before that, you have to put 2 elements on the stack. So we'll get x and then we'll get y. So now we got position in memory, but there is something interesting in WebAssembly. The memory access doesn't is not per 4 bytes, like in 32 bits, but 1 byte. So basically, one value will take 4 bytes because it's 32 bit, aka 4 bytes. So we will have to multiply it by 4, which is, I just get a constant, it's 4, and then we multiply it. And now we get to access the memory, which is a command which is i32.load, and we basically passed all the tests. So we took coordinates, we got our index, we multiplied it by 4, and we got the index in memory, and load basically gets it there. And then the next thing I'm gonna do, I'm gonna just copy paste pretty much this code, because the next thing is called store cell. So what it's gonna do all the same operations, but instead of loading, it's gonna just store them. There's like magic load answer button, so you can see like it's exactly the same, and then you just store it. One thing I'm doing a bit different here is because we always storing like the current step. I'm gonna get global step instead of passing a y coordinate. So we're kind of like halfway through. I'll start speeding things up a little bit. Um, the next thing is shift. So we are gonna get 3 values there, and there will be some, I'll just load the answer here. But what we're gonna do is we're gonna do some binary shifting, which is fun thing. So if you take a number, and then in JavaScript it would look like this. You shift it to shift left to 2 positions. So in decimal system, it would be pretty much like multiplying by 100. So we get this x 0 0. Then we're doing similar thing with y. So we get y 0, and then we don't have to shift z. So the reason it's helpful is we can add those things together, and we basically get x, y, z. So what we're doing here is we're taking 3 numbers, let's say 101, and we're returning a number which is 101 in binary. Next thing is just loading previous cell. So we get x, and then we look at the previous cell, like what was happening there. I'll load a couple more functions. Get cell score is basically going to look at the cell. Let me see if I have tests. So what it's gonna do is look at the cell. It will look at all 3 neighbors. It will get their values using load previous cell from memory, and then it will get this binary number. So it's literally like look at last 3 numbers before the cell and get a number which is like 101, for example. And now the fun thing starts. We're gonna add a thing called table. So what table allows us to do is first class functions in WebAssembly. So the way it would work is we create 2 functions. One is called enable and one is called disable, and they're like super simple. All enable does, it returns 1, which is true, and then all disable does is returns 0, aka like false. And then we use an lm command, and we have a map of 8 values, where the first one happens if we have 0 0 0, the second one happens if we have 0 0 1, and so on. So they are basically 8 functions, and at any point we can say call function with an index of 1, for example, and then it will call this one, and it will get the value of 1. So here, this is basically those 8 rules that we saw before. That's what it is. Next thing, there are like 3 more functions. There is one where we just evolve the cell. So we look at the cell, we get score of its neighbors, and then we call this call and direct, get into this table of 8 things, and pick the one which returns 1 or 0. So basically get the score of the cell. The next thing will evolve the whole row. It's interesting because it actually has a loop. Loop is WebAssembly. In WebAssembly is actually pretty crazy. It's you have a block thing, and then you have a loop thing, and then you kind of break into that. I'm not even going to go too deep here. What's interesting here, and I give you like a few seconds to think about, who can tell me what those instructions are? So you get something, you add 1, and then you kind of, I can say, set, and then get. Okay, anybody has any idea what this would look like in JavaScript? I++. Yes, okay, you're getting a sticker with Angular as a token of appreciation. So yeah, so this is literally I++. This is what you have to do in WebAssembly to get the same result. So what this loop does, it basically iterates over the row size. So until row size equals this I, we're going to just call this evolve cell thing. And then the last, we're coming to the end, the last thing is evolve, which evolves multiple times. It takes 1 parameter, which is how many steps we're gonna go down. It still has a loop. It still has this I++ thing. It also has a step plus plus thing because we want to increase step with every step. And that's pretty much it. It should pass all the tests at this point. So we can see the result on the right. So we have row size of 5. This is why it's small. But just to see that it works, I'm gonna look at the rule which is like 0, 0, 1, which is for this cell, and I'm going to disable it. So now we can see like this becomes disabled. So now we can do something with 1, 1, 0. And let's disable this one. Yeah, so it kind of becomes more interesting. Let me disable something else just randomly. I don't know what happens. Yeah, so we get some like really weird behavior. The cool thing is now we get to run it full screen since we don't need this code anymore. So here is the configuration. We have the size of the cell, so I can make it like a bit larger or smaller. We have width and height of the screen. We have row size, where you can add more things. This is row size from WebAssembly. And then we have rules. So the way rules are calculated, it takes this number, it converts it to binary, and then it pads with 0. So 1 is 0, 0, 0, 0, 0, 0, 1. So rule 0, it will be like all zeros. And then you can see it's just empty one poor cell. And then rule 2, this will just go here. So it's just binary. There are like, I'll just scroll through some rules just so you can see what's going on. Some of them are less interesting than others, and some of them are kind of like more fun. So this is pretty boring. Here is like a little Tetris figurine, which is like kind of going to the right. This is also kind of interesting. So the more interesting ones, like this one, is rule 90. So this is a famous fractal. It's called Sierpinski Triangle. It's called by the name of like Polish dude who kind of first thought of it. And it basically goes like this, making triangles larger and larger. I can probably add, make the row size larger, maybe 150. Okay, and then the size of this thing smaller. Cool. Yeah, so you can see that it. Let's do more steps. Yeah, you can see it basically goes like this. The next interesting thing is like rule 110, which kind of looks similar. Oh, it looks similar because I put in the wrong thing. So the interesting thing about this rule is that somebody actually was able to prove that this rule is Turing complete, which means that specifying specific inputs, you can actually do calculations. It will probably take like a couple trillion steps to get results, but you can like add numbers. You can even like implement cellular automata using this thing. I don't know why anybody would be doing this, but it's basically like a little computer inside of cellular automata. I'm not explaining how it's working, it's very complex, but also fun. Like if it sounds interesting, I recommend reading a Wikipedia on it at least. The next rule is 184, which I put in the wrong thing again. Not what I expected. Let me see if I can find a similar rule anywhere. Okay, we'll skip rule 184. I like how live coding pretty much worked and like this doesn't work. But it's finally time for the rule 30, the weird, the chaotic one, which really confused Richard Feynman. It basically looks like this. So it's pretty random. It is possible to take this column and then run random generator tests on it, and a lot of tests actually will pass, so it's kind of like pseudo-random thing. And then by specifying different starting configuration, you can actually get like different columns and different values, which is pretty interesting. But yeah, so it's basically like a bunch of triangles going there. Cellular automata is not limited just by those things. It's all about like we have a bunch of cells, we have a bunch of rules, and they evolve. So probably some of you seen like Game of Life. created by a guy whose name is Conway, and he kind of regretted it later because he did so much stuff, and everybody only knows this one thing about him, Game of Life. Game of Life is like, I'm not showing anything, but it's like super immense and complex, and like really crazy stuff, and it's also Turing complete. So somebody implemented Game of Life in Game of Life, and it was like, maybe I can have time. Let me see if I can find meta pixel Game of Life. Okay. So the rules are, we are looking at the 8 cells around, and it's a 2D thing. And then based on how many of the cells around are dead or alive, the cell either becomes dead or alive. And then people spend like years trying to come up with patterns. So we can see there are like some moving things here. There is actually a music. Let me see if I can make it louder. Yeah, so this square is like 2000 by 2000 cells. So you can see like the whole thing is pretty huge, like millions. And it also takes like, it probably like sped up like 100 times because it seems like pretty fast. But at some point they are gonna, so this is a cell and they are gonna like switch the cells, and like some will die and some will kinda be born. Okay, it's coming, it's coming. Okay, here you go. Have you seen that? Yeah, so it basically, oh, it did it again. So with the idea about cellular automata, like the cool thing is like the rules are super simple. I can explain it to you in like 2 minutes, but then the behavior is like super complex and it's like really hard to understand why. And this is basically what this book is about, New Kind of Science. Fun thing, anybody been to Cambridge? They actually are using, I think this is rule 30 as a decoration. And I'm pretty sure like some of the programmers would pass by and like, oh, yo, that's cool. I've seen that before. So if you ever are in Cambridge, you'll be like, I know what this is. I don't have much time, but there is a little explanation about how this whole thing is encoded in binary. It pretty much goes 1-to-1. There is a nicer visualization where you can click. So it's like a bunch of ones and zeros, and then they map to those things. So it literally says like, so if the number is 1, for example, here it stands for imports. If it's 2, it's type. If it's 3, in memory, and so on. And then it basically shows the thing. It's not very complicated, but I won't be able to explain it in 40 seconds. There is a cool thing called WebAssembly Studio. Basically what it allows you to do is create a project in any language. And as I mentioned before, like what we're doing today is very hardcore. You probably won't do it day to day, but I'm gonna start an empty assembly script project. So what assembly script is, it's a subset of TypeScript. So the idea is like it can be compiled to WebAssembly. So we have like a very simple file, which is like it has a function which is say hello, and we have a function called add, which we've seen before. Can probably make it larger. And now when I build it, it's gonna build a wasm file out of it. But if we look inside, then most of the things we actually seen before. So here is function add. We export it. It takes 2 parameters. It produces a result, and then it gets 2 local things and adds them together. Like at this time, it probably should be pretty clear what's going on here. And then basically whatever you compile like pretty hardcore things into WebAssembly, but the basic structure will be like very, very similar. So now you should be able to kind of jump in and say, oh, at least I know like this is a function. I know like what's going on here. And this should be the last slide. I would like thanks Stefan, which was supposed to give me a laptop because mine wouldn't connect, but then my connected, miracle. Thanks a lot for AV, guys. And thanks Armada JS team again. Yeah, and this is my Twitter handle. I'm going to post slides at some point if somebody thinks their like head is not broken enough yet. And I'm curious if anybody has any questions. This is where you would post them. I can just look at it now. Thanks, everybody.
Thank you, Kirill. So this was really, really interesting talk, and we do have some questions.
Yeah.
So first question is, what's your favorite language for writing WebAssembly?
I like while working on this talk, I actually got a little bit into Rust, and it kind of break my brain. It has like very interesting approach to garbage collection, where like most of the languages are like use your variables, and then at some point you stop using it, and we'll figure it out somehow, and it doesn't exactly work. And like in JavaScript, it's sometimes a problem when like garbage collector would just jump in and start doing weird stuff. There's like a whole science of garbage collection, I guess, because of JavaScript. What Rust does, it says you can only have one reference to any variable. So if you want another reference, like go clone it. If you don't need it anymore, you pass it to a function, destroy it. And this kind of changed the way you write code, but this also kind of supposed to speed things up dramatically, and just the approach is kind of mind-blowing. It's you have to learn new paradigm to just write very simple things. And Rust is the language by Mozilla, which also is like heavily involved in WebAssembly. So yeah, Rust is pretty cool.
Okay, and now we have...
Oh, my favorite question.
we have 3 questions actually that are pretty much the same. So why should you use this? How is this useful in real life? And what is the real life usefulness of this?
Yeah, so there are 2 things. First, WebAssembly. And second, like this weird thing which I did here. So WebAssembly is, as I mentioned in the previous slide, it can be compiled from any language, so it's kind of intermediate thing which you can run anywhere. There was a really cool article by, I think it was Fastly, and they have a thing called Lucid. I don't know if I can find it. Fastly, and they were talking about how they started. Let me see if that's it. Yeah, so basically what they do is they allow you to run WebAssembly on the edge in the cloud. And then you can, of course, run JavaScript in the cloud. But in order to run JavaScript in the cloud, they basically have to start V8, which is pretty heavy. And here's an example. So they say we start this WebAssembly environment, and it takes us like 50 microseconds. But then if you start Chrome, then not Chrome, but like the V8 engine to run JavaScript, and basically takes like 100 times more. So it's kind of very simple, as I showed today. Like the actual language is like super simple, and you don't have to parse it, first of all, because it's binaries, so you basically just like read it through. While JavaScript, it takes some time to load the V8, to figure out what's going on in the file, parse it, and then only then you run it. So you pretty much get like very, very fast cloud functions, which is cool. And then again, you can compile it from any language. And then you can also run it in any language. And WebAssembly doesn't have types, but it doesn't mean that it cannot take things of types. Basically what happens is a language passes something to WebAssembly, let's say a string, and WebAssembly has a special type called like anything, anyref, I think. And it's just like, I don't know what to do with it, and I'm not gonna touch it. But if anybody else asks me to return it, I know how to return it, and that's how they do it. And then there are mappings between different languages. So you can write something in Rust, and then you can run it in Python, and you can pass data in between languages. And the same with JavaScript. So JavaScript with WebAssembly before, this part of passing stuff between was very slow, and now it's actually is pretty fast. Why do we need digging into what and cellular automata? Well, I guess I can talk a little bit about cellular automata. The interesting property of it is this evolution thing, where you cannot predict what happened on row 100 without seeing the first 99. And this basically allows it to be used in like say cryptography. There were like some attempts to do like blockchain. For me, it's mostly fun. If you look, I highly recommend looking at Game of Lives. There are things which are being invented like right now, like certain pattern which behaves in certain way. There was something like in 2016, it was like a big deal. Somebody came up with a thing which just like moves, but it has to take like specific amount of steps to do that. And why do it together? It's first of all, it's fun. Second, it's at some point you will hear WebAssembly, and I I hope that you'll be like a little bit less afraid now when you see what's inside, because it probably won't get like much harder than this. Like we went like pretty hardcore right now. We kind of wrote raw WebAssembly. If you ever get to do any hardcore stuff, like you compile something and it doesn't work, and this actually happened to me when preparing the talk. I was writing some code and it just wouldn't work. So I went into the what and I look what's going on there, then I go into binary, and then I figure out, oh, this is why it doesn't work. So now you have necessary tools in mind, and you know that it's possible that you can work with this thing. It's also like recently they showed the debugging capabilities for this. So it's similar to JavaScript. You can jump into functions, you can stop, you can see like what the values are. I didn't have time to show it, but it's also possible. So what I'm trying to do is like I want to put on your mental map what's inside of WebAssembly. And then once you actually need it, you probably forget everything, but you know like what to look up for. That's it.
So we did a full cycle now. We started with assembler, and then we were going more and more abstract, only to come back to assembler. And the last question, or maybe it's a statement. There are 3 claps. Maybe Outer want to explain what this means. Otherwise, I think it's a final clap for our.
There is one more question that I can answer quick. Is how does Conway's game of life relate to this? It's basically exactly the same concepts. You have cells, you have grid, you have rules, and you have evolution. That's it. There are like much more fancier things with like hexagons, very complex rules. There are things you can like generate beautiful pictures, like somebody did like cellular automata art. So that's how it relates. This cellular automata thing is about cells and evolution. And yeah, I guess now is this. Yeah. Thanks everybody.
Thank you.